slides after the today's meeting. So as was communicated earlier on, we have now begun the series of regression, and basically are going to look at the 3 regression types. Of course, there are several others that you could consider, but we'll do the linear regression, we'll do the logistic regression, binary with interest on a binary outcome, and then finally get to do the survivor analysis, and that would cover the foundational regression types that for the most type are usually used. And if any reasons wants to do something that is complicated, of course, we can work on the sidelines in that regard. So with that said, what is regression? What do we understand is regression? Okay. Trying to see who I can. Kavila, I see you unmuted. Do you want to explain to us?
Yes, I want to. Yeah, so regression, this is a model that we use to predict the value of the outcome or the dependent variable, depending on the information that we have about the independent variable. And this also depends on the measurement scale of the dependent variable. Thank
you. Good, thank you. Any other comments?
Yes, just wanted to add.
Sure, go ahead.
Yes, just also to say that this model that my colleague has mentioned also allows us to account for confounding factors. So then we are able to adjust for them. Thanks.
Okay, sure, thank you. So thank you for those comments. So basically, in medicine, we're often concerned with relationships between variables, right? For example, if you have patients that are attending a clinic, would be interested in trying to figure out whether their blood pressure is related to their weight, or whether in a group of patients that have type 2 diabetes, whether the circumference of their waist is related to their fasting glucose. And mostly there are different things we can do to try and define this relationship, right? Depending, as Kavila has said, on the scale of the outcome that we're trying to find out or to explain. And so with regards to linear regression, when the outcome in that regard is continuous, some of the methods that we can use to define that relationship when you have 2 quantitative variables is correlation and linear regression. And so maybe a question that we'd ask is, what is the difference between correlation and linear regression? So this is a recap. You guys have learned this, so I don't need to to go on someone. Francis, do you want to give a response?
Good afternoon. Am I audible?
Yes, please.
Yes, I just wanted to respond on correlation. So correlation actually measures the strength and the direction of a linear relationship. That's my understanding.
And how does it differ from regression, from linear relationship, from a linear regression?
I think linear regression, it analyzes the relationship between a dependent variable, which is on the y-axis, and the independent variable, which is on the x-axis.
Okay, sure, thank you. So correlation basically, as has been said, you are trying to measure the strength and direction of a linear relationship. Basically, in the example that we have blood pressure and weight, when blood pressure is increasing, does the weight also increase? And is this increase in the same direction, or does blood pressure increase and weight reduce? And so that's the correlation that you'd be measuring. But for regression, basically what you're trying to do is you're trying to model or to summarize and basically quantify this relationship. So correlation just tells you that when X increases, Y increases by this proportion, and it is in this direction. But you have to go a step further to actually understand that relationship. And that's what your regression will do by basically summarizing that through a formula and then quantifying what that increase would be for your blood pressure for every unit increase in weight. And then you can take account of other variables that could also explain that relationship. And so ideally, regression will do more than what your correlation would basically do. So broadly speaking, when we're talking about linear regression, there are basically two goals that we can use, and perhaps for other linear for other regressions as well. So the first approach is what we call as prediction, and in this approach, we want to fit what we term as a predictive model to a data set. And then once we've developed that data set, with that model, we can then use it to make predictions about an outcome from a new set of explanatory variables. Or you could use your model to explain, right? You fit a model and then you try and explain what the interrelationship might be between a set of variables. In that regard, oftentimes we usually just use our models for explanation, right? The odds are XY compared for males compared to females, holding all other factors constant. But we can use those models really to predict certain parameters, and this will be part of what we'll do in this course. So for a linear regression, the scale of the outcome variable is really very important because it has to be continuous, right? It has to be linear, it has to increase in a continuous manner. And in this figure below, basically it unifies the terms that we will use in this lecture as we review. So the outcome, has already been said, is basically the variable that is of interest to us, and it is oftentimes called by other names such as dependent variable or response variable, or you can also say the predicted variable. And we usually put it in the y-axis, as Francis did say. And your explanatory variables of interest basically are sometimes, of course, called the exposure, the predictor, or the independent variable, depending on what type of model you're trying to use, whether it's predictive or explanatory. And these are usually put on the x-axis in that regard. And in this example, we'll be using the waist circumference for a type 2 diabetic. So in simple linear regression, basically we have one explanatory variable, and we usually try to call this as univariate linear regression. And as we all know, basically for linear regression, what we're trying to do is to draw a linear line to summarize what this relationship basically would be. And this linear line is the best fit line. And there's an error term that is associated with this linear line, which basically is the average distance that each of the points that you have in your data set falls away from your linear line. We'll talk about this maybe in a little bit more detail. But what I would also want to mention, when you have more than one explanatory variable, you can call this as multivariable regression model. I've heard, perhaps maybe it's the way lectures are taught, I've heard, especially for this group, using the word multivariate regression. So to try and perhaps make a distinction between multivariable and multivariate, we'll start by explaining the term covariate. Have any of you guys heard the term covariate, and what does it mean? I'll be calling out people's names today. So the sooner you volunteer, the better. Kelvin, have you heard of the term covariate, and what does it mean? Makapush.
Hello, good afternoon, Mr. Warren.
Hi.
How are you?
Doing well, thanks.
Yes, come again. I didn't hear your question.
So my question is, have you heard of the term covariate, and what does it mean?
Okay, the way I understand it, yes, in statistics I've heard about it. A covariant variable, usually it's a variable, or it's a continuous variable that is actually not part of the experimental manipulation and has no effect on the dependent variable.
Okay, thank you. Sanda, I see your hand is up.
Good afternoon.
Afternoon.
So just to add on what Mwakapushi has said, it's a variable that has a possibility to predict the outcome, but it's not the primary variable of interest. I think.
Okay, sure. Anyone wants to add?
Yes, Mr. Warren, can I be right if I say that a covariate may be a confounding variable?
Yes, so it can be a confounding variable. That is right, yeah. So I like asking these questions just to kind of like get a sense of how you guys understand certain concepts. So please do research on that so that we can go back to what we're looking at here. So multivariate basically means that you have several outcomes in that regard. And so we would basically want to avoid using that term, because for most of the regression models that you do, you have only one outcome, right, that you're looking at, and this is being explained for by a multiple variable. And so you're most collectively going to use the word multivariable model as opposed to multivariate regression. You can compare these terms in your own time and actually see that these are different approaches in regression. So anyway, back to what we're looking at. So when you're developing a regression model, basically it provides you with estimates of uncertainty, and these we often like to call them as standard errors, right? And also since your regression model is basically a subset or a sample of a larger population, you can also provide the 95% confidence interval of what your values would be in the true population, and whether that point estimate is basically statistically significant. And we have explained standard errors before, that basically they represent the average distance that the observed values are clustered around the regression line. In that regard, to just summarize what that relationship would be. So other elements that, of course, we are interested in is the intercept, the beta naught, which is in the regression of a linear regression, is basically the point where the regression line cuts the y-axis, and it represents the mean value of the response or the outcome variable when all the explanatory variables are equal to 0. And so in our example, if we are looking at type 2 diabetes patients and their fasting glucose levels in millimoles per liter, we would define that relationship as is shown here, right? And where the regression line cuts the y-axis, which is beta, basically in that regard would be 1.5 millimoles per liter. And then you begin now, for every increase in the circumference of the waist, you begin to add 5.8 milliliters millimoles per liter. And so that's how you basically define your regression relationship. And so, as we said, the response variable has to be continuous, and the beta naught is basically the intercept or the constant, the mean value of the response when the experimental variables are equal to 0. For linear regression and perhaps for other models, there are times that you want to make the intercept meaningful, especially if none of your continuous variables have a value of 0. And we'll try and do this in our example so that we can have a meaningful intercept. And so for you to do that, there's a concept that is called mean centering. This is where a continuous variable, as one of the continuous independent variables, right, is mean centered. Basically, you subtract the mean value from each of the observed points that you have, such that the beta, which is beta naught, which is the intercept, will represent the mean value of that continuous variable in that regard instead of a 0. So it becomes a little bit more interpretable and would be meaningful. And you see what that is like when we get to do our example. It can be a confusing concept, but you appreciate it in the example that we will do. And as we did say, B1 is, of course, a regression line slope, which is an increase or a decrease in Y corresponding to 1 unit increase in X. So let's take our example. We have an outcome variable Y and an independent variable X, and we define this regression relationship. Right, as we said, when X increases by 1 unit, whatever that unit would be, Y would increase by the value of beta 1. And this is not only an increase, it can indeed be a decrease in that regard. So let's take the example that we've been talking about. How would we explain the beta 1 in this example, which is the 5.8 millimoles per liter? So I just want to check who can explain this for us. Okay, who hasn't said anything so far? We can go to Martin. Martin? So I want you to explain it in the concept of 1 unit increase and so on and so forth. Martin, are you there? Okay, if Martin is having problems unmuting, can we go to Leah?
Yeah. So what I understand is, like, for every 1 unit increase in the waste, the fasting glucose level increases by 5.8 units, by 5.8 millimoles per liter.
Okay, thank you. So that is right, but you have to specify what that 1 unit increase basically would be. So it's what for every 1 centimeter increase, which is your 1 unit increase, right? Because our waist circumference is in centimeters. Of a type 2 diabetic patient, the corresponding increase would in their fasting glucose basically would be 5.8 millimoles per liter. So just to specify what that 1 unit increase would basically be. And of course, you can stratify this by adding more explanatory variables. And in this example, what we have done is to add sex to try and see if there are any differences in this increase by whether one is male or female. And our regression line then would become as is shown here. And so since we have to choose one reference group, our reference group in this regard would be the males who would code as 0, and then the comparing group would be the females who would code as 1. So it means that the values that we would get when we add the intercept and whatever the circumference would be for the males would have to multiply the 2.5, which is the sex, by 0 if you want to calculate for males. And then it becomes 2.7 when it is for females. So what we are saying is it should be actually been the other way around, right? I don't know how I label this. The males should have been the zeros and 1, because on average, the females are 2.7, have 2.7 more levels of fasting glucose than the males. Anyway, with that said, the whole essence is to show this distinction that is there, that depending on which group you choose, you have to multiply the other one by 0 and multiply the other one by a 1, and that would be the distinction, and everything else remains as it is. You calculate what the waist of that individual would be, and then get the value. If they're female, you'd get what that waist would be, and then you add a 2.5. If they're males, you just get what their waist would be and the intercept, and then you'd get what their fasting glucose level would basically be. And you can add, of course, a host of other categorical or ordinal explanatory variables, and you can continue adding as much as you can, depending on what your variables might be in that regard. So with that said, we also need to understand what approaches is used when we're fitting a linear regression. And the approach that is used is basically one that is referred to as the ordinary least squares. So if you get a point and for every increase that you have in X, there's a corresponding increase that you'd have in Y. Basically, the regression model will do that for each of the points that you have in your data. It will calculate what that distance might be, right? And then get to find the regression line that minimizes all these distances, so that the sum of the list of the squares of these is actually the least values that you'd have. I hope that makes sense to you. And then these differences are basically what we call your residuals in that regard, such that they have a mean value of 0, or they almost cancel out in that regard. And based on that, you can also compute a statistic, the coefficients of determination, which you often like to refer to as your adjusted R squared. Your R squared, and when you have multiple variables, you call it as adjusted. So basically, this is a proportion of the variance in your Y, which is your outcome variable, that is explained for by your independent variable in that regard. And we use the R squared for model diagnostics, such as goodness of fit, in addition to other variables in addition to other fit statistics that we can look at. So linear regression basically has a number of assumptions, and I just want to check with you if you guys remember these assumptions. Okay, so who hasn't said anything? Geoffrey, do you remember any one of the assumptions for linear regression?
Yes, Mr. Warren.
Okay.
Yes, I do remember.
Okay,
The
which
number
one do you
one
remember?
assumption is that the number one assumption is that data must follow linearity.
Okay.
So the relationship between X and the mean should be linear.
Okay, good. Thanks for that. So linearity assumption, right? So which is of course the first assumption, because you're going to do a linear regression, there has to be a linear relationship between the X and Y. And so this is important, and you can use your correlation to try and see whether a linear relationship does actually exist between your two variables. Okay, so let's go to the next assumption. Which assumptions do we have, Helen? Do you remember any one of the assumptions for linear regression?
The variables should be normally distributed, or there should be normality.
Okay.
Hello?
Sure. So there's the normality assumption. Do you want to explain that?
Like all the variables should be normally distributed. Like they should be normally distributed, meaning they should assume the bell shape when plotted.
Okay. All right. So maybe let me ask, because that is maybe the third assumption that I was gonna show. Let's see. Okay, that's good. We'll get back to that and just try and clarify that in a little bit. Abdul, do you want to say the other assumption for linear regression? Oh, seem to have lost.
Mr. Warren, before Dr. Abdo comes in,
Sure.
maybe the other assumption should be that observations are supposed to be independent.
What does that mean?
So the meaning is that the value of one observation should not affect the value of another observation.
Okay, thank you. We'll get back to that. I think we've lost Dr. Abdul. Patricia, which other assumption do you remember for linear regression? Patricia, are you with us? Okay, looks like Patricia has dropped off. Ruth, do you want to bail out Patricia? Okay, Webster. Okay, Patricia,
Hello.
I think, yeah, Ruth, please go ahead.
There's equal variance of residue for any value of x, or hemodynamicity.
Okay, thank you. Webster, did you want to say something?
Yes, the other one is that there should be no multiple linearity.
Okay, perfect. Thank you. So you guys at least remember your notes. I'm very happy. Okay, so there's independence of assumption, right? So the observed independent, each observation should be statistically independent of each other. What this simply means is that the residuals are not correlated to each other. There are, of course, other approaches when you find that your residuals are correlated that you can implement, for example, multi-level models, which of course we won't look at, but those could get to handle your correlated data. An example of that is, take for instance, you're going to measure a before and after intervention. You know that the after outcome, right, after the value after an intervention will be rated to your baseline value, because that is what you started with. And so in that regard, statistical independence could not be assumed, and you have to look at other models that would take account of that non-independence in terms of the residuals. Or for example, if you're going to get patients from different hospitals, perhaps some of the differences could be explained because of the hospitals that they're coming from, right? Some hospitals might have better doctors than others, and so certain conditions will be better treated in other hospitals than others. And so that could also explain that some points are not statistically independent. And so you have to check for that in your model. Normality assumption that Helen talked about, there's a useful rule, right? What she stated, right? That your continuous variables should be normally distributed. That's a useful rule, but it, in most strict sense, right? It is actually the residuals that should be normally distributed, right? Because it is this concept that is critical for the hypothesis testing and the construction of your confidence interval. even if your independent variables were not normally distributed, you could use your Pearson correlation, and if it reports that these variables are correlated, despite taking care, without taking account of their level of distribution, you can still do a linear regression in that regard. So that's just something that we need to be aware of. But if your independent and dependent variables are both normally distributed, then it's even better that way. In that regard. Homoscedasticity that Luth talked about, right? This is the equal variance across all levels of the independent variable. So what this simply means is that your residuals should basically be roughly distributed and should, of course, be related to your normality assumptions. And non-multicollinearity, for this, we're basically trying to explain that the independent variables are not highly correlated one to another. What this means is that, two or more variables in the same regression models basically would be considered to be correlated if you cannot distinguish their independent contribution when it comes to predicting the outcome variable. An example of multicollinearity might be if you include in the same model both age and categorized age, right? So those two variables will be highly correlated because age would almost always predict what the categorical age would be. And perhaps we'll try and show you this in this model. Stata by default would drop those models that are highly correlated, but R doesn't do that. And so you have to check for that assumption and just make sure that your models are not, your variables are not correlated in that regard. So it's good you guys remember all this. But as we did say, for linear regression, basically these we often use them hand in hand with correlation because we want to, first of all, check the first assumption, right? The linearity assumption, before we even go ahead to do our linear regression. And so we would use, if our continuous variables follow a normal distribution, would of course use the Pearson correlation, which takes account of the distribution of the variables. But if not, you can of course also use the Pearson correlation if you do not want to take account of the parametric nature of the data. I heard someone say hello. Did someone have a question? Oh, maybe not. Okay.
No, it was just a mistake. Apologies.
Okay, sure, thanks. Okay, so when it comes to interpretation of p-values, I think we did a very good job previously to try and explain this. But basically, we have a cutoff of 0.05 where we get to indicate whether something is significant. And you may have seen, in some outputs where you have 1 star, you have 2 stars, and you have 3 stars. Basically, this relates to how strong the evidence is against the null hypothesis, and whether it ranges within that category, or it's less than 0.01, and then you'd have your 3 stars. But I thought we just remind each other with that. You can look at these when the notes are shared. So coming now to our example for today. So medical expenses are one of the major recurring expenses in human life, as you might imagine, right? It's common knowledge that one's lifestyle and various physical parameters dictate disease and also the ailments that they can have. And these, of course, would then dictate the medical expenses that one would incur over their lifetime. So according to various studies, major factors that contribute to higher expenses in a person's life include smoking, age, and their BMI. But we do know that the right to health and other health-related human rights are legally binding commitments that are enshrined in the international human rights instruments of the WHO, in that every human being has a right to the highest attainable standard of physical and mental health. In developing countries, however, this is often limited, and we have a variety of challenges which significantly contribute as to whether someone's overall health or well-being is well. So I'll just pause this for a moment so that I can take up a call just for a moment. Okay, apologies about that, right? So in developing countries, access to health is, however, often limited due to a variety of changes which significantly impact on the overall health and well-being of the population. And some of the barriers include high cost of health services and also a lack of insurance by the urban poor. So given the above, the National Health Insurance Management Authority is thinking of ways to optimize services, especially for the urban poor. So one way to do this is by ensuring that NEMA collects sufficient funds in premiums than it spends on beneficiaries' medical care, but still make these premiums affordable. Medical expenses are, however, difficult to estimate because the most costly conditions are rare and seemingly random. Still, some conditions are more prevalent for certain segments of the population. For instance, lung cancer is more likely amongst smokers than non-smokers, and heart disease amongst those that are obese. So this is more of our background information to our study question for today. And so what is our problem statement? As an epidemiologist, you've been assigned by the Minister of Health to sit on a technical working group reviewing NEMA's premiums. Your task is to review patient data to estimate the average medical care expenses given a policyholder's medical and social-demographic characteristics. And the minister wants to understand the following. One, the minister wants to understand what the correlation between medical expenses and the person's attributes are, and which attributes best predict medical expenses. Two, the minister wants to understand what a policyholder, such as a recently recruited female nurse aged 21 years of age, has one child and has a BMI of 36.7 kgs per square meters, would typically pay as premiums. And three, what NEMA may reasonably charge at monthly premiums on policyholders' medical and social demographic, depending on the medical and social demographic characteristics of policyholder. And for this, the minister has asked that you develop an actuarial table of premiums by sex, age group, number of children, smoker status, and BMI of policyholders. Disclaimer, this is a simulated exercise that was developed by the author and does not in any way reflect true information. So do we understand what our study question is for today? So we're doing a bit of health economics today. I thought this is more of an appropriate example that we could use to try and explain the concept of that we have today. Okay, just one more. So do we all understand our scenario for today? I hope I'm communicating because I'm not getting any responses.
It's loud and clear, but we've not yet grasped the concept. I'm sure we'll get to understand it as we go along with the practical aspect.
Okay, perfect. Yeah. So the session that we're going to do will now have a mix. Okay. So I'll work with you to go through the analysis. everything that you need to answer the 3 questions. I'm going to help you answer question number 1, but I'll give question number 2 and question number 3 as an assignment that you, of course, we'll discuss as a group in the next session. And so maybe as we go through the data, we'll try and explain some of the concepts and what I want you to do in this example. So I hope you understand as you look at the data. Okay, so with that said, I did share with you a data set and an R Markdown file. And so today we'll be using an R Markdown. Let me see, someone is busy annotating on my screen. Yeah, okay. That's not me, by the way. Yeah, so I did share with you an RMD file, R Markdown file, and also a data set ahead of this schedule. So the data set has the following variables. It has age, which basically is the age of the patient in years. It has the sex coded as 1 for females and 0 for males. It has the hospital, where the patient sought care, and the 3 hospitals that are there are 0 for Mainasoko, 1 for Levi Mwanawasa University Teaching Hospital, and 2 for the University Teaching Hospital. Children basically is the number of children or dependents that are on the scheme, and these range from those that do not have any children to up to greater than 3 children on the medical scheme. And then whether the policyholder is a smoker or not, and what their BMI would be, and then the associated medical expenses that they have incurred in the previous year. And so we'll use this data to answer the interest that the minister has based on the scenario that has been presented here in that regard. Okay, and so with that said, we can go to our linear regression. Okay, so I'll just stop sharing and then go ahead, and I think those are quite good. Okay, so share. Okay. All right. So there's a concept of best fit model in that regard, and we'll try and talk about this because this is the bridge that is often there between your bivariable model, which has only one independent variable, and how it is that you move from that model to a multivariable model, the one that has several variables. And there are several regression techniques that you can use for selecting your model. And I think most statisticians will agree that in statistics, there's a concept of parsimony that is often applied. Do any of you guys understand or have an idea of what this concept might be? I hope I'm communicating. I'm not getting any responses from anyone. Dr. Mchimba, have you ever heard of the concept of parsimony? Abdul, can you hear me?
Hello, I was saying no, this is my first time hearing of it.
Okay, all right. Oh, okay. Yeah, because I was getting worried. I thought I was talking to myself. Okay, so anyway.
Yes, Warden, I can hear you.
Oh, okay, great. Have you ever heard of this concept of parsimony?
Yes, I've come across it. It's a concept of explaining any concept in the simplest of terms.
Exactly, right. So I often like to give a few examples in this regard. So one example, if you hear a howling sound, what would you think of right? And so think of the most simplistic way. Is it a wolf or is it a dog, right? So think of a dog instead of a wolf. So basically what this concept is about is that, when you have a host of many phenomena that can explain things, researchers must always accept the simplest and most logical of them to prevent explaining in many complex theories. Simply put, if you can't explain it simply enough, it means you don't understand it. Right. If you're going to Lusaka, use the most direct route and don't start going to Kasama, then you go to Muingu, then you go to Mansa, then you go to it's a long road, right? Use the most direct and simpler way to explain concepts. And so the motivation for me bringing this is that, and I think some of you have heard me say this for this cohort. I think your cohort was the first to try and do the most complex of models, which really there's nothing wrong in that. But sometimes, the most basic models that we do, but you do it well and you do it fine and explain things, is much more helpful to you than trying to burden yourself with even the most complicated things that you want to do. But that is not to discourage you not to do complex things. If you have the ability to do it, by all means do it. But you understand that for the most part, whatever, no matter how complex statistics you're going to do, at the end of the time is how do you simplify it so that people are able to understand and appreciate it, because you're sharing this out to the larger population, some of whom are not as conversant as you are with your statistics. So how do you simply explain that concept? Or if you like, there's a mallet hammer, right? A hammer that, those guys who put tiles use. If you want to crack a nut, what do you use? Do you use a sledgehammer? Do you use a simple hammer? Because the more complex the model you're using when you're analyzing your statistics, the more strained it will be, and most likely it is to break. And so before you think of complex models, what is the most simplistic model that can explain this? And then you can build up to that model. And that's why we thought we go back to linear regression, try and emphasize some of the concepts, and then we move on to the more complex model. Because by and large, in whatever complex model you're looking at, a simple parsimonious model accomplishes a desired level explanation or prediction with as fewer variables as is possible. Oftentimes we hear residents asking us, okay, so how many models should I have in my how many independent variables should I have in my model? And so whenever you're thinking of that, try and think of parsimony to try and try and avoid overfitting the model, and of course also underfitting the model, because really this comes in when you're trying to look at the model goodness of fit. So going back now to what it is that we're discussing. So we're trying to bridge the gap between a bivariable model and a multivariable model. So how do you decide from your multivariable model? So bivariable model, how do you decide which variables you carry over to the multivariable model? So there are several approaches that you can use in that regard. One is, of course, looking at p-values. By default, we usually use significance level of 0.05, but for us to include a variable in the multivariable model, we usually want to look at what its p-value is. And so if a p-value is 0.2 and below, by variable model, we'll include it in the multivariable model because potentially it could be affecting that model. So that's one consideration that we could use. Another consideration is to include priori variables, right? These may or may not meet this cutoff of 0.2, but these could be based on theoretical relevance to our study, or what literature has said that these are significant variables when it comes to predicting a certain outcome. And so you would want to consider including such variables. Other approaches that you can use is to try and compare what are often called as nested models. So these are models that have a subset of the covariates. So you have your model that includes all the variables that you think are important, and then you start removing all those that are not significant and try and compare which of these models fits better. And there are different approaches that we can use for that. We'll look at this example in our example, right? So you just don't fit a model and then go on about and say, no, I've developed this model. You always have to diagnose your model, right? You might not need to show all these in your results, but of course you can include them as appendices to your analysis. But just mention that, you looked at diagnosis of A, B, C, D, and D, and perhaps your analytic project, refer to them in your appendices, or if you want, in your manuscript. And if you think it's important to show them, you show them as supplementary materials. But basically, a good model is one that fits the data well. But what does fit the data well mean? One way to look at this is to, of course, expect that, your fitted values, these are the values that your model is predicting, are, of course, in close agreement with the observed values. You're basically training a model and say, when someone has this age, this sex, this BMI, whether they're a smoker or not, then their cost should basically be so much. And so that so much cost should be close to what it has observed in the data in that regard. So to do that in linear regression, we use a set of values, right? Values for our covariates to try and predict what the outcome would basically be. And some of the model fit statistics that we look at are the following. One is the log likelihood value. Does anyone understand what that fit statistic is for the model? Or has anyone ever heard of it? I know you have. Patricia? Patricia, are you there?
Yes, I can get you.
Okay, all right. Does anyone want to try and explain what the log likelihood value would be? Or it's the first time we're hearing about it? Okay, maybe not. Okay, so the log likelihood value basically is, and you guessed it right, there's the term log here, right? And that's a natural logarithm of what is called as the likelihood function. So in simpler terms, this is the joint probability of observing the given data under the model's assumption and parameters. And depending on the model that you're looking at, this value is calculated differently. We epidemiologists won't, of course, bother ourselves so much in trying to figure out how this is done. But it is important that we understand, because we need to apply it by and large. So for a linear model, as we explained when we were showing you that line and how the residuals are calculated, basically what the log likelihood value does is to minimize the sum of the least or the ordinary least squares, right? The residuals, so that at the end of the day, they will lower the value of the log likelihood is the better fit, right? The model would be. And this is by default one of the values that the model will calculate for you, and you can retrieve it from there, from the model information. The next metric that would look at in the terms of linear regression is what is called the coefficient of determination, which is the R squared. And I know you guys know what this one is. Does anyone want to help us and explain what this is? I see William has joined. William, would you want to help us with what the R squared would be? Is? Or anyone in the group? Are you guys seeing this term for the first time? I'm sorry, I have to ask because I'm getting worried now.
What's the question again, Warren?
Did anyone get the question?
I did.
Okay, could you help me, please? Could you help me?
Please repeat the question.
He asked us to explain what the coefficient of determination is. I can go ahead to answer or
Yeah, sure,
attempt
please.
to answer.
Yeah, please go ahead.
So it's a statistical measure which is used to assess how well the regression model explains the variability of the dependent variable.
Perfect. Thank you, Susan, for that. So, oftentimes you use this in linear regression. There are other coefficients of determination depending on the type of model that you're looking at. But basically, in linear model, the coefficient of determination, or what we usually like to call as R squared, is basically the proportion of the variability in the outcome that is explained from the independent variables. And so when you have one variable, your R squared and your adjusted R squared will be the same. But when you have multiple variables, those will be different. And so you would want to report on the adjusted R squared, and we'll look at how to do this in the model. So this is a value that is measured from 0 to 1. So if your R squared is 0, it means that whatever variability that is there in your outcome variable, that your independent variable is not explaining any one of them. But the closer the value is to 1, it would then mean that the largest part that the variability that your outcome variable has is being explained for by those independent variables. And so I'll give you a hint that what I'm explaining now and coloration answers the first question. So please do pay attention because this is important. Yeah, with regards to the first question that we asked, with regards to the minister wanting to find out what the correlation is between the cost and the patient attributes, and which of the patient attributes can best explain the medical costs that are there. So another parameter that we basically look at is the archaic information criteria, the AIC. Does anyone have an idea what this is? I deliberately put a formula there because I want to try and explain this to you so that maybe that could be. I'm trying to avoid going into hard statistics, but I thought the easiest way to explain this is by looking at the formula, because really that's how easy you'd understand it. AIC, does anyone want to explain it? Okay, who are we calling? Danny, do you want to explain this? There are some residents that are in noisy rooms, so they are unable to unmute. What do you understand by AIC? And of course, this is correlated to the BIC, so we can maybe already bring that in. Okay, how much time do we have? Okay, so 1 hour 30 minutes. Does anyone want to maybe give some explanation to us what they use the AIC and the BIC for? I see there's Moria. Moria, do you want to help the class? Okay. Now I'm getting worried. Are you guys coming across these terms for the very first time?
Yes, Warren. For me, it's the first time.
Oh, okay.
Yes.
For me, yeah, I think for me, I've come across AIC and BIC, but really understanding it fully, yeah, I think this would be my best opportunity.
Okay, that's fine. Okay, so whenever you run a model, of course, not all models will generate an AIC for you, but the typical ones that we do, linear regression, logistic regression, and survival analysis, Poisson models, there are these two metrics that the model will report, the AIC archaic information criterion and the Bayesian information criterion. So let's try and break this down for you so that you understand and why these are important, that you consider them when it comes to model diagnostic. Right. So the AIC is basically a model selection metric, right? It helps to identify the model that best balances two metrics. One, the fit of the model, and to explain what a model, best fit model is the one that fits most closely, the values that it has predicted most closely fits the observed values. So besides model fitment, it also looks at how simple or complex your model is, right? So how many parameters is your model going to explain? So in explaining the AIC and why we have to look at it, the lower the value of the AIC is, the better fit the model is, and we'll compare the variables that we have in our data set to try and see which one is what values it is reporting. So this is an absolute value, and you basically compare it amongst themselves, right? So if you have two models, you compare the AIC, and the model with the lowest AIC is the one that basically fits the data better. The reason for this is the following. So let me see if I can try and alternate this. Your log L value is basically your log likelihood value. So what your model does is that it gets the log likelihood value of the model, which, as we did explain, is the joint probability of of fitting the best fit line for your data. So by default, this best fit line should not be influenced by other parameters, right? But oftentimes there are more parameters that we add. And so the more parameters that you add, which is your K value, the model is predicting, then you are penalizing, right? You are increasing because your log value is negative. So when you add log value, the negative value, and you see that when you do the model, it's negative. It's always negative. And so negative times negative gives you a positive. And so whatever the base value of the model is, the more parameters you are predicting, which is represented by the K value here, then it means that you're increasing on your log likelihood value. The model is trying to strain to take account of the parameters that you're putting in your regression. So as if, say, for instance, you have 3 parameters that you're estimating, then your model will have to take account in generating that best fit line. It has to take account of sex, of age, and whether someone is a smoker. If you add another variable, for example, hospital, then again it has to adjust and take account of that. So your log likelihood value therefore gets to increase the more parameters that you increase, and then your AIC values gets bigger. So basically, your AIC value is trying to report that balance between your best fit line and the strain that just to undergo in order to accommodate all the K values or the parameters that you put into the model. Is that clear? Does that help you? You'll see this when we go to the regression model. The BIC is also similar, and both of these statistics usually are reported by the regression. Again, let me try and wrap some of these things. Okay, so your BIC is similar to the AIC, only that it uses the Bayesian approach, but basically also has a similar log likelihood function. And instead of using a 2 here, it instead uses the natural logarithm of the number of observations that you have in your model. The model that we have has 386, is it? Or 89? I'm blanking out on the number. I think 89 or 86 anyway, around the 80 something. So it's going to take the natural logarithm of the number of observations that you have. And so this value will be much higher than the 2 that is there. And so the model is therefore penalizing much more when you have more parameters in your model. So oftentimes the BIC will always be higher than your AIC, but both of them are used to compare and contrast between the model that you have developed and other model parameters. When we come to regression, you understand this a little bit further, but these are absolute values, and you compare them one with another and then try and see how they're coming out. And the smaller the value, the better it is. It means that the model did not strain in the largest way possible to try and fit your best fit line. I think from my understanding, that's how you'd best explain your AIC and your BIC. But these oftentimes, regression, survival analysis, linear regression, Poisson models, and a host of other models as well, including multi-level models, you often want to look at your AIC and BIC value and choose a model with the least of these two values. I hope that's helpful. And of course, you have to check that your model meets your assumption that you have listed. For linear regression, you have to check the assumptions that we talked about, that those assumptions are being met. And if it is not being met, then perhaps another model regression you'd have to apply. Is that helpful in explaining this concept? Please do read more. Martin, you have a question?
Yes, Mr. Wallen. I think thank you for the explanation of the Bayesian information criteria and the archaic information criteria. But my question is, in the model fit, when you produce the output in regression, is it the same that explains the adjusted R squared? Because I'm seeing similarities in the way it's explained when the adjusted R squared is produced, because it tells us how much the variation of the dependent variable is determined by the addition of the independent variables. Could it be the explanation to these two criterion to the adjusted R squared?
They're different, right? They're different because yeah, for this one, you're looking at the number of parameters that you have in your model. So these parameters, maybe that's one thing I didn't do. What when I say parameters, what do I mean? So if you're not going to put any independent or predictor variables in your model, there's what we call the null model, without any predictors. There are two things that your model is to generate. One, it will generate for you the intercept estimates and also the standard errors. So by default, even in a null model, it will still be able to calculate for you the AIC and the BIC. And the K values by default, the minimum value that you can have is 2, which is basically your intercept and also your standard errors. Then if you add one predictor value, your K becomes 3, because you'll be estimating the intercept, the standard errors, and then the estimates for that third predictor, and so on and so forth. So the more predictors you have, the larger your K becomes in that regard. And it's similar to this. But your adjusted R squared, the model is just basically trying to look at, okay, you have this predictor, you have this predictor, you have that predictor. Of these predictors that we have, which one best explain the variabilities that we have in the model? I'm not going to break it down for you, but the formulas are different in how these parameters are calculated. What is important for you to do is just to explain them. You don't need to worry yourselves with the formulas. But for me, oftentimes, when you have two models, right, there are certain times that you have a model where in one model, the AIC is low, but the BIC is higher. And then in the other model, the AIC is high, but the BIC is lower. And then you are conflicted. I'm saying, okay, this model A, has lower AIC and higher BIC. And then model B has higher BIC and lower, higher AIC, but lower BIC. So which one do I choose? So the understanding of basically these two parametrics will help you to decide. Are you going to look for complexity, which the Bayesian model will penalize? If your model is more complex, it has more parameters that it is estimating, it will be penalized much more than what your archaic information criteria will do. The coefficient of determination R squared basically just looking at the proportion of variability. And we worry so much about it in linear regression. When you talk about logistic regression, there's the pseudo R squared. And oftentimes we don't worry about it so much because it's very, very small. And there are other fit diagnostics that we need to look at. You see, we have to look at, the rock curve and other things that we'll look at when we come to logistic regression. But basically, it's just the variability. So if your adjusted R squared is, for example, 0.72, right? So you're saying this variable is explaining about 72% of the variability that we have in the outcome. It's as simple as that. And that's the explanation that you need to understand and not worry so much about the formula. Then the AIC and saying, you compare the model A to model B based on the AIC and the BIC, and the model with the lowest AIC was this model, and therefore you went for this model. And that's the application that as epidemiologists oftentimes would want to go for. And so all those helps us to choose the best fit model and not just do your regression and then you go and say, okay, I've run my model, but what diagnostic did you use to try and choose and see that actually these are the best fit model? I hope that's helpful in answering your question.
Yes, sir. Thank you.
Perfect. Right. So I think we've explained more about the log likelihood value. And with all these statistics, of course, there are always cautions, right? The log likelihood value, the more parameters you have, the more likely that it will become larger. Please do read these notes, but the key really is that you can compare models based on the log likelihood value. The closer it is, because it's negative, the closer it is to zero, the better the fit. The further it is away from zero, then it is the less better fit the model is. And you can actually run a log likelihood ratio test to try and compare two models, provided they are nested. And when we mean nested, we mean that one model is a subset of the other, right? If you have a model that has sex, age, and BMI, and then you have a model that has sex, age, BMI, and smoker. The one that doesn't have a smoker is a nest of the larger model, or a subset, as we've used it here. It has the same variables, but one has extra variables, and it is using the same data set in that regard. And so you can compare the log likelihood value, which has an I hypothesis that both the full model that has all the variables that you're testing and the one that has a subset of the variables, or a nested model, equally fit the data. And because they equally fit the data, by the concept of parsimony, the simpler model should be used, and therefore you'd go for the nested model. But if your p-value is significant, it means that the full model fits the data significantly better than the null model, and therefore you'd have to use the full model in that regard. And we'll try and do this in R, and the function that you use is log likelihood ratio test in that regard. We talked about coefficient of determination, basically proportion of variability that is explained by model. And as we did say, this value trends towards 1. So the closer the value is to 1, it means that variable explains the larger proportion of the variability in the outcome variable. Okay, so just to recap, what then are the model building approaches, right? How you select which variables to include in your multivariable model is basically of concern to many analysts, including you, me. This is something that you always have to do. And just to recap, you always have to be mindful that you don't always need to overfit your model. So the more parameters you add in your model, the potential is for your overfitting, and you can't basically control for everything. That's the general rule, right? But again, you can't have too simplistic a model because it won't again explain all of the variability that you're seeing in your model, and or else your model will become highly biased. And you can see that by looking at a combination of all these metrics. So when you're running your model, you have to look at all these fit statistics, as they often call them. What is your log likelihood value? What is your ARC and BIC? What is your adjusted R squared? And then compare these metrics and then try and choose which of these models would basically be the same. So to wrap it all up, when we're trying to move from a bivariable model to a multivariable model, the approach that we'd use is, one, include all parameters that have a p-value that is less than 0.2, right, into your multivariable model. Include priority variables that are of interest to the study, that either literature have said that they are significant variables, or variables that are of theoretical relevance. And that's why you really have to think about your hypothesis. Okay, I have this variable sex. When I include it, is there a difference between the cost of charges between males and females? I think there is. Why is that? Right. Besides a male and a female having the same medical care, a female would have to attend, prenatal and postnatal care, and therefore most likely the cost would be higher, and therefore I would expect that the medical costs would be higher for females, and therefore it makes sense for me to include that variable in the model. Yeah, so that's the kind of like conversation that you should be having, and not just look at your p-value and say, oh no, it is significant, it is not significant, let me add it. So try and think above and beyond just the p-value and also think of statistical and theoretical relevance, and also literature, what literature says about those variables. So then once you've decided on those variables, the mistake that many of us make is just to throw everything into your model. And sometimes you have a model, a variable that is creating some noise or is straining your model. Strain to strain. Yeah, so instead what you should do is you should include explanatory variables beginning with the most significant p-value, and then you begin to add them that way, which of some people often called as investigator-led approaches, right? We've already talked about the theoretical or literature relevance in that regard. And then once you've added, you try and see how your model is performing, you check its fit statistics, and then get to choose based on your log value, ARC, and your adjusted fit value. And then check if your model is overfitted, if there were any p-values that drastically changed, and whether that is warranted. And like we said, a parsimonious model is better. The less complex your model is, the better it is. And these will, of course, be reported for by your fit statistics that you always need to check. For linear regression, these are the fit statistics. When you look at logistic regression, we'll look at what fit statistics you should be looking out for. And so be mindful of that. I'm trying to look at the time. What time do you guys want us to stop? 16 or 16:30? I don't know. It's not a tricky question. Okay.
16:30.
Okay, so I think let's reach a stage where we're able to do the first question in our study scenario, and then I'll let you explore the other. You have the slides, and you have the analysis. So I'll try and ask you to just explore answering the second and the third question, because everything is there in the analysis. I think the last bit that I was supposed to talk about is if we're going to have 30 minutes after 14:30, we should have enough time, is what is called a stepwise regression, right? So similar to what we've said about model building, you can use the software to help you choose the best fit model. I'll talk about the criticisms and all about that, but first let's understand what it is that we're talking about, right? So you can of course, use what is called as in a stepwise way, right? Removing or adding independent variables into your model. And there are two things that you use, basically the AIC and the BIC, and also the p-values, and to try and see how these values change overall as you add or remove variables into your multivariable model. And basically, the goal of this is to try and find a model that best fits the data, as is reported by the fit statistics that we talked about: log likelihood, adjusted R-squared, AIC, and BIC in that regard. So there are basically two methods. Let's not confuse you with the terminologies. Investigator-led is what I explained, right? You look at your variables at your independent variables by variable model. Okay, so which one is the most significant? Let me enter it into the model. Which one is the next one? I enter it, and then what are the fit statistics? And you keep on adding until you reach a stage where maybe your AIC and BIC has increased than the previous model. Then you choose that as your best fit model. That is what we call as investigator-led stepwise selection or elimination, depending on what it is that you're doing. So these forward stepwise selection, backward stepwise selection, or stepwise selection are basically similar approaches. It's only how the model is entering or removing independent variables into the model. For stepwise regression, it is beginning with a model without any predictors, and then it begins to add. Backward, it begins with a model with all the variables, and then it begins to remove. Stepwise, it begins with a model without any predictors, and then it adds, and then tries and see if it can remove at the same time. And you see all this in R, and it will be much more clearer. I think R does a better job at explaining these processes than Stata would. And so you understand this in a little bit more. And of course, there are pros and cons to using investigator-led, right? So the pros are that you'd look at literature and you have a good understanding of the causal relationship that are there between your variables and your outcome. But the cons are that there's risk of underfitting or even overfitting, because you might just look at these variables and think that these are the best fit independent variables, but maybe there are other variables that could explain your model better. For the computer-led, I also talk about the pros and cons, but as I said, forward selection, you begin with a model without covariates or a null model, and then you start adding each variable one by one, and then try and see until you get the best AIC and BIC. And also log likelihood value, right? You keep adding, and then you keep checking your AIC. We'll show you how the model does this in R. Yeah, until you reach your best optimal variables in your model with the least AIC and BIC. For backward, you begin with all your variables, and then you begin removing them from your model until you reach the model with the least AIC and BIC value, or you've specified the stopping value based on the p-value. So you'd have only removed two variables, and then the others remain, because that's the one that gives you the best fit model based on the fit statistics, AIC and BIC. Stepwise, you put in the model, put in another variable, and then try and see if you can remove any variable and try and see if it's there's better fit. So I'm doing both of them at one time. I know it can be confusing, but don't worry about it. You understand this better in R. So what are the pros and cons? The pros are that it's when you're using, maybe before I come to this, so you can, for me, the advice is that use stepwise. But basically, whether you're using backward stepwise or forward stepwise or both, by and large, these models, these steps should all converge at the same model. And so oftentimes people just use stepwise because I think from the logic point, it's much more easier and straightforward. And it makes sense for you to add something and then try and see if there's something that you can remove, as opposed to just going one direction, as it were. Yeah, so the last bit, and this is the last slide that we have, the pros and cons. the pros is that when you're using the computer, the stepwise, it's easy to apply. It improves model generalizability, and it will always yield you the model that best fits the data, and you're able to implement this objective. And also because the computer is doing this, it's reproducible, as opposed to investigator-led, which might be subjective, right? I might lead only a certain subset of my literature and not lead one literature that says that a hospital where someone goes would impact on the cost. And because I didn't find any literature supporting that outcome, I might not add that independent variable because I don't have literature or the priori knowledge. But the stepwise will be able to do that for me by looking at the AIC and BIC. However, the major criticism is that, the computer does not have understanding of the causal relationship that you as a researcher has. It just looks at AIC and BIC and use that to determine which ones are the best fit model. So the best is for you to do investigator-led and try and compare if the model that you have chosen is indeed the best model when you compare to what the PC would basically do. And so with that, this brings us to the end of the theory. And so let's do the bit. The other bit, we'll try to find time to do them later, but let's do the bit up to where we're able to answer the first question. So to recap, let's just go to the question that we're trying to answer so that it makes sense what it is that we're trying to do. And I hope I haven't lost you. Discard. Oops. Okay, seems like it's cutting. Okay, so if you recall, this is the scenario that we're looking at, right? And we're trying to answer 3 questions from this study. 1, the correlation between medical expenses and patient attributes, and which of those attributes basically best predict medical expenses. And then to try and give the minister, okay, we have this person who's a nurse, a female nurse, they're age 21, they have 1 child, and they have a BMI of 34.7 kgs per square millimeters. What would be the premium typically? And then basically give the minister a table. If someone is female, this would be the minimum premium, and this would be the confidence interval. So those would be basically be the actual tables that we'll be looking at. If someone is of this age group, if the age group less than 29 years of age, this would be their premium, and this would be the 95% confidence interval, and so on and so forth. So that's the exercise that we'll be doing. I'll help you do the easy part, 1, and then I'll allow you guys to do the second and the third part, and get to present those results in our next sessions, just to get you thinking about what it is that we have learned. Is that clear? I hope it is. Okay, so let's head back to R and try to answer the question that the minister asked, right? So the minister asked a question: what is the correlation between medical expenses and the patient's attribute? We did run our correlation test, right? Where is that? I'm missing out on the, oh, it's here. So how would we answer the minister? So this was the correlation test that we ran. So how would we report this to the minister? Maybe let's read this one. So does anyone want to have a go at this report? Remember, we compared the correlation between medical charges and BMI, and medical charges and age. So what would be our report to the minister? Does anyone want to have a go at the response? Have I lost people? Danny, do you want to have a go at this? So which variables are correlated to medical expenses? Does anyone want to help? Danny? Okay, I seem to have lost people. I'm getting worried.
Mr. Oren.
Yes.
Yes. You're asking about which variables in this scenario.
Mm-hmm.
Yes, we are looking at one, the age.
Okay.
Of this lady. Is it 21 years?
No, we're answering question number 1. We haven't come to question number 2 as at yet.
Yeah, so the age, the parity, maybe the number of children, including the body weight. Hello?
Hi. What are our variables, Kelvin? What variables do we have in our data set?
I said the age, the sex,
Mm-hmm.
and the weight.
I don't think we have weight in our data set. We have BMI though. Yeah, of course you can derive your weight if we knew, but we have BMI. So you remember
age, sex.
Mm-hmm.
Yes, the variables I'm saying we have age, sex, hospital, number of children, and then even smoking status.
Mm-hmm.
Yes.
Okay. So remember when you're doing correlation, what should be the scale of your variables? Do you guys remember? Come on, I know you know this, guys. What should be the scale of your variables when you're doing correlation? Should they be categorical? Should they be continuous? Should they be ordinal or what? Leah, what should they do? What should they be?
Try. I think for the linear regression, the dependent
For correlation. For correlation, we're looking at correlation.
or for correlation, they should be continuous variables.
Okay, perfect. Yes. So there should be continuous variables. So the variables that we're going to look at basically are, we know that our outcome is the charges, right? The medical expenses. And so the only variables that would then test for correlation should either be the BMI or the age, which are the two continuous variables that we have in our data set. And if you remember, we did run, let's do that again, right? We did run declaration. So let's call this one BMI so that it's clear to people, right? And then we can call the other one age. So we'll run the correlation between medical expenses and the BMI, and the correlation between age and medical expenses. And then we can, of course, try and see what it is that we are getting from these two tests. So the first question, remember, is the minister wants to know what the correlation is between medical expenses and patient attributes. And so we need to ask ourselves the question, which patient attributes can we use to find correlation? They have to be continuous attributes. So those attributes would then become the BMI and age. Are we together thus far? I'm guessing we are. Okay, so so we can check first the so the correlation between medical expenses and BMI is about 0.86, right? And that is the confidence interval that we have, and the significant p-value that we have there. And the next is for age, right? So it tells us that the correlation is 0.71. That's the 95% confidence interval, and the p-value is that. And if you use the report part, you will see that, you know, for BMI, the correlation is large and significant. For age, the correlation is small, but yet nonetheless significant. And the minister's question, if you recall, she's saying of these patient attributes, which one best predict medical expenses? And so the question we should be asking ourselves is, since both age and BMI have a significant correlation, which one of these two would best predict medical expenses? Are we able to answer that from a correlation test? I hope I'm not losing people. Are we able to answer that? The last part, we know which attributes, right? From the question, we know which attributes are correlated. We know that BMI is correlated to medical charges, and that correlation is large. Age is correlated to medical expenses, and their correlation is small. But the question that the minister asks is, of these correlations, which one best predicts medical expenses? So are we able to explain that from the correlation test that we have done? Are we able to choose between age and BMI, which one of these two would best predict medical expenses? Is the question clear to everyone now? Helen, is the question clear? Okay. I'm not getting any response. So I don't know if I'm being heard or I've lost my audio.
Yes, it's very clear.
Oh, okay, thank you. Yeah.
Yes.
Okay. Yeah. So remember Pearson correlation, or even if you're looking at
Sorry.
Okay, sure. Thank you. Yeah, I need that feedback because you know, this is a virtual platform, so I might be talking to myself, not knowing that I've lost people. Yeah. So from Pearson correlation, we cannot be able to answer the second part of the question, which of these two variables best predict medical expenses, because correlation is just telling us that, you know, when age increases, the BMI, sorry, the medical expenses also increase, but that increase gives us the direction of that increase. But again, the relationship is small. Although it's significant, it's small. For BMI, the relationship is large and significant, but we don't know what that relationship is. And so for us to be able to answer between age and BMI, which of these two best predict medical expenses, would have to go to the regression. And that's why oftentimes linear, correlation just shows that there is a relationship, and this relationship either increasing or decreasing, and that's so that you can answer. So in part, we know that as someone's age increases, the medical expenses will also increase. Also, as someone's BMI increases, the medical expenses will also increase. But to what extent, to what value that increase is, we're not able to answer that from the correlation test. We only know what that ratio of increase is. That's what the raw from that correlation reports to us. And so we'd have to go to the regression now to be able to define and quantify that relationship so that we're able to answer that question. I hope you guys are now following up. That's why regression answers much more than what the correlation would do. And so if you guys remember, we did run these bivariable models, each one of them as they were. Okay, so let me include that because we'll need it. Oops, apologies for that. Yeah, so we need age because it's important. We're trying to answer the means-test question. So we did run each one of these bivariable models before we go to the multivariable model. We've also run age, and there's an output there. So I said initially that, and we'll be finishing at 16:30. Don't worry. I say that, this approach, you'd have to run each one of these models separately and then look at the output for each of these models individually. But the GT summary package, Great Table Summary as they call it, does a better job. It can combine all these models for you so that it comes in one easily formatted table that we often want to present them to. And for that function, we use TBL univariate regression. The other one need to be TBL regression or regress or something like that. We'll check it out. But this one is UV, which is basically univariate regression. So you specify the data set and then select the variables that you want to include to generate bivariable or univariate models for. And you specify the method. We'll use GLM. I'll explain all this in our next session to become much more clearer. So we use the generalized linear regression model, and we specify the family, which is the Gaussian for linear regression. And these are just functions that we have. We want our estimates to be to 4 decimal places. We want the p-value to have 3 decimal places. We want it to be bored at 0.05 and so on and so forth. And once we've done that, I add this to an object called GT bivariable bvar. So it's Great Table bivariable. I noticed that last time people got confused between these objects, and so I'm just trying to make sure that when we have a object that is starting with GT, we know it's a Great Table object. It's not a model like the way we have here. When you call it bvar, we know it's a bivariable model with an outcome, with an independent variable for sex. And so I hope that is helpful naming. Okay, so we'll go ahead and run that for you, and you will of course be able to get your model. It takes a bit of time because it has to basically run each one of these models one after another. And if you compare, you realize that these would be similar to the ones that you generated here. But what we like about this is it gives them much more clarity, right? Compared to females, that would be the cost, right? On average for females, holding all other independent variables constant, right? But this is not significant because our p-value is greater than 0.05. So it can be a reduction of that much in cost, or it can be a higher cost of more than 2,800 kwacha, or a reduction in compared to males of 1,000 of over 1,300. Again, for age groups, that's what you have. For the number of children on the scheme, these are the different costs that you have. But remember, these are independent models. You're only accounting for that specific variables. I'll come and explain this to you in a little bit more details, depending on the hospitals. So basically, whether someone went to Mainasoko, Levi Mwanawasa, or UTH, there wasn't any statistical difference in that regard. But there was statistical difference if someone was a smoker, by almost 5,000 costs in their medical expenses. And if someone 1 unit increase in their BMI, right, there was an increase in cost of 1,516 kwacha in the year. Remember, these are annual costs that someone incurred in that regard. So we are trying to answer the minister's question, and this is the last bit that will help us answer. So what we're going to do is we're going now to get the fit statistic by just looking at the bivariable model. Because correlation, you're not taking account of, you're not controlling for other variables. So we just look at the bivariable models and then try and answer the first question. So what we'll do is we'll create a table that shows what the different fit statistics are for the model. So we'll calculate the log likelihood value, row bind, and then calculate for each of the different models that we calculated, right? Hospital, sex, age group, child, number of children, smoker, and BMI. I've created here what I'm calling a now model. So this is a model without any predictors. So if you do a model without any predictors, what the model is just basically calculating for you is the mean value of the outcome, and then creates what that mean value would be in the true population in that regard. And I'll show you this if you want that. So when we run that and do the sum, and I hope I'm not confusing you guys, please do let me know if I've lost you. I've seen there's some questions. What I'm doing will answer some of those questions. So you're getting this mean value. So this is the mean. It's telling you that this is the intercept, but basically this is the mean value of our estimates. So I want it to report the 95% confidence interval. Let me just get that confit. Yeah. So when we run that, it gives you the mean value and the 95% confidence interval. If you don't believe me, the other way to do this is to use the descriptive tool, and we use the mean CI. And then we specify our data set, right? Charges. What that will do, it will report to, I don't like the way it's coming out. Let's use this package. Okay. This one is a bit, yeah. So look at that. So if you remember, I'll just copy this and put them here for you so that you understand what, when you say the now model without any predictors. So when you run your now model without any predictors, the estimates that you get, right, 28, it's basically that cost and your confidence interval. So basically a now model without any predictors, it's basically just calculating what the mean value of the costs are and the 95% confidence interval, what it would be in the true population. And these are basically the same. I hope you're with me. So I have included a now model. So basically just without taking account of whether someone has gone to a hospital, what hospital they went to, whether they are female, whether they have this age group, whether they have children, what based on the data that we would have, what would be the mean value and what is the 95% confidence interval. That's what we're doing. So that's what the now model basically does. So we'll calculate the log likelihood, we calculate the AIC, and then we'll calculate the BIC. And then basically we also get to calculate the adjusted R squared. So for this one, there's a function called R squared where it pulls the R squared from the model, and then I'm just calculating it as a percentage to 2 decimal places because I'm rounding that. Please do have a look at those values. And BIC, once you have a model, you can specify AIC and then need to pull the AIC from that model. If you do BIC, to pull the BIC from that model. And then I'm going to combine this column bind here, and then we have, for each one of these. And then now I'm going to name what is 1, 2, 3, and 4, and then these other parameters that I have here. So that's what I do, row names and column names, and we have this. I hope you guys are with me. So the now model has a log likelihood value of negative 4, 41, 49 point that, and that's our AIC and that's our BIC end. Because we don't have any predictors, our adjusted R squared will basically be 0 because we don't have any independent variable to explain the variability. All that we're doing is we are calculating what the mean value would be, and that is expected. Okay, so now let's go ahead and compare. So the variable hospital is explaining, remember we converted these into percentages because we multiplied them by 100. It is explaining only 0.7% of the variability in the medical expenses. Sex is explaining 0.3%. Age group is explaining 3.43%. Children, 3.7%. Smoker, 5.78%. But the BMI is explaining the largest of the variability, which is 74.84% in the model. Is everyone with me? And with that, we can even see that it has the lowest, the log likelihood value that is closest to 0, or the largest if you want, and also the lowest AIC and BIC values compared to the other models. There was a question in the chat, how small should the AIC and the BIC be? There is no absolute value, but these are relative values. You compare them one with another. Depending on the model that you are using, these values can be anything. But if they're the same models of the same data, then you can compare them as we are doing right here. So for these models, they're around the 8,000 and 7,000. And the one that has a comparatively lower value, the better the model is. But remember, these are by variable model. And then we can also look at the BIC and AIC. There's a question, Leah, that does it imply the fewer independent variables, the better the model is? Not necessarily. We'll answer that question when we come to the multivariable model. But basically, by just looking at this by variable model, my inclination to answer the minister's question would be, when you look at the question that she asked, would say that looking at the medical expenses, the patient's BMI and age are correlated with medical expenses, but the BMI is the one that best predicts what? Medical expenses, because it accounts for nearly what? 74.85% of the variability in medical expenses. So whatever the medical expenses would be, 74.85% of whatever the medical expenses would be explained for by the BMI. And so what does that tell us? We need to encourage people to look after their weight so that they're not obese, because the better we manage people's BMI, then the better we will at managing what the medical expenses would be. And that would be a recommendation to the minister. So I hope that gets to answer your this question, and we can pause there for questions. We'll continue this again to try and answer question 2 and question 3. I'll ask you to explore these questions. Everything that you need is in the slides that, in the, what do you call this? In the script that I've shared with you. So hopefully you guys will be able to answer those questions. I hope you will as we get to meet. So maybe let me pause there in case there are any questions that you might be interested in asking. I hope I haven't lost people, because if people don't ask questions when we've been talking for a while,